Hello everyone, this video is going to cover the topic of equilibrium. And remember, we've actually used the term equilibrium already this year. When we were talking about dynamics, we said that an object was in equilibrium if the net force acting on it is zero. But now that we are also allowing objects to rotate, we need to add a second condition to equilibrium, that the net torque on the object is also zero. So it's not accelerating translationally, but it also does not have any angular acceleration. You'll sometimes also see the term static equilibrium. What that means is that in addition to the net force and the net torque both being zero, V and omega are also zero. And so it is not just that the object is not changing the way that it's moving through space or rotating, but it is also at rest both translationally and rotationally. One thing that is very convenient about problems where the net torque equals zero is that if the net torque equals zero with respect to one axis of rotation, it equals zero with respect to all rotation axes. And this greatly simplifies equilibrium problems relative to the more general case where the net torque is not equal to zero. Remember that torque depends on the relationship between the pivot point, or the rotation axis, and the force being applied to the object, and so different rotation axes could give us different torques. But if the net torque is zero for one axis, it's zero for all axes. From here, these problems actually look a lot like the problems that we've talked about earlier, where we need to employ both F net equals ma and tau net equals I alpha. But again, here in equilibrium, we know net force always equals zero and net torque always equals zero. One very common example that we'll see of an equilibrium problem is a problem involving a seesaw. So let's say that we have a 2-meter long seesaw. And we have a person at one end, and we have a person on the other end. The mass of the person on the left is 40 kilograms. The mass of the person on the right is 30 kilograms. And the mass of the seesaw itself is 20 kilograms. And we want to determine how far from the left edge the fulcrum should be placed in order to keep the seesaw in equilibrium. One thing to note, since the mass of the person on the left edge is greater than the mass of the person on the right edge, we know the fulcrum is going to have to be someplace to the left of the middle in order for there to be any chance of this seesaw remaining balanced, remaining in equilibrium. And if we say that the length of the seesaw is 2 meters, we're looking to find this distance x from the left edge to the location of the fulcrum. So if we draw a free body diagram for the seesaw, we have a total of 4 forces. We have the weight of the person on the left pointing downward at the left edge. We have the mass of the person on the right, or the weight of the person on the right pointing down at the right edge. We also have the weight of the seesaw itself pointing downward, and that's going to be applied at the center of gravity or center of mass. And assuming this is a uniform seesaw, that's going to be directly in the geometric center of the seesaw. And finally, we have a normal force upward from the fulcrum. We're going to assume that the seesaw is very narrow, and so we're not going to worry about the thickness or the height of the seesaw. And so we'll place all of these points at the same vertical position, and we know that the net force points upward from that point. And we can draw in all the distances that we know here. We have that distance x that we're looking for from the left edge to where the normal force is applied, a distance of 1 meter from the left edge to where the weight of the seesaw is applied, and then finally 2 meters from the left edge to the right edge. There are a couple of ways that we could go about doing this. One would be to say we can find the normal force that the fulcrum exerts using F net equals 0 and use the measurements that we've seen there. I'm going to show a different way of doing it here based on the fact that we know 3 of the forces and we don't know one other. We don't know that normal force. And so very often the easiest way algebraically to solve one of these equilibrium problems is to place the pivot point at the point where a force that you don't know is applied. Remember, torque equals Rf sine phi. If R equals 0, meaning that the force is applied at the same point as the pivot point, then that force can't exert any torque no matter how big it is. And so I'm going to say that the pivot point here is the actual pivot point of the seesaw if it were to start rotating at the fulcrum. We know net torque equals 0, or we could write that as torque from the person on the left plus torque from the person on the right plus torque from the weight of the seesaw itself plus torque from the normal force, which as we discussed is 0. For all of these vectors, the r vector is going to point horizontally, all of the force vectors point vertically, so it will be 90 degrees for the value of phi for all of them. The other thing we need to be careful of is we need to make sure that we get our signs correct. So choosing the fulcrum as the pivot point, the weight of the person on the left is going to give us a counterclockwise or positive torque. It is a distance x away from the fulcrum, force of m sub l times g, as we discussed, times sine 90. The other 2 forces are going to give us clockwise or negative torques around the fulcrum, So for the person on the right, that force is being applied a distance of 2 meters minus x away from the fulcrum, m sub r times g times sine 90. And then finally, for the weight of the seesaw itself, that is a distance of 1 meter minus x from the fulcrum times mass of the seesaw times g times sine 90, all equals 0. Notice that we can factor out a sine 90, which then cancels, and we can factor out a g, which then cancels. So now we need to rearrange to solve for x. So we have m sub l times x minus 2 meters times m sub r minus x, or minus m sub r times x. Sorry, that should be a plus sign. Minus 1 meter times the mass of the seesaw plus mass of the seesaw times x, all equals 0. We want all the terms with x on one side, all the terms without x on the other side. So we get m sub l times x plus m sub r times x plus m sub s times x equals 2 meters times m sub r plus 1 meter times m sub s. Factor out an x on the left-hand side, divide by what is left. We get that x equals 2 meters times m sub r plus 1 meter times m sub s divided by the total mass. Plug all of our masses in. Mass of the child on the right equals 30 kilograms. Mass of the seesaw is 20 kilograms. And mass of the person on the right is 40 kilograms. And when we plug that all in, we get a value of x of 0.889 meters. And as a sanity check, we can see at the very least that x is less than 1 meter. And so as we would expected, the fulcrum needs to be placed closer to the more massive person on the left-hand side rather than the less massive person on the right. Notice also we could have been told to treat the seesaw as massless, in which case we just would not have the weight of the seesaw itself at the center of mass being involved in applying its own torque. So this is one of the common types of equilibrium problems, the seesaw problem, or any situation where you have some horizontal object with perhaps some other weights or other forces applied to it, and we're trying to see the conditions under which that system remains in equilibrium. There's another very common type of problem which we will cover in the next video.